Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. We're in chapter 2, which is double and triple integrals. We're doing section 2.2, which is double integrals over general regions now. Last lecture we showed how to define this double integral over a general region D, and we did a couple examples. Today what we're going to do is a couple more examples of type 1 and 2. Example 1. This example I'm going to take the time to remind you that if I have a positive surface, which this is a function of two variables, the graph of that will be a positive surface. And then if I take a region, even if it's arbitrary, we can talk about the volume of below the surface, this guy, and above a region D. And then what they can cleverly do is rephrase that slightly even more and say, I can phrase describing a prism that way. And so that this is what they're doing. They're saying, find the volume of the prism, see the picture, whose base is the triangle in the plane, this guy. So first I draw the triangle in the plane for myself, so then I've got an idea. It says the x-axis, which is kind of mean, which is y equals 0. Then it's the line y equals x, and the line x equals 1. Now I have my triangle. Then what I have to do is move that into the three-dimensional picture. And then what they're saying is I have a surface, the graph of that is going to be this plane, and that's what it says. The top of that lies in the plane, this guy. So now what we're doing essentially is finding the volume up below the surface Z and above the region D, which happens to give us a prism. And then we're going to find the volume of that prism. How do we do that? We now have bounds. This tells me that from our picture, our region D is going from, X is going from 0 to 1, and Y is going from 0 to X in the picture. And again, you have to decide every time for yourself. When you look at it, you have to say, am I going to phrase this in terms of y as functions of x or x as functions of y? But in these courses, we're only going to give you those type 2 regions or type 1 region. Therefore, this is what? Type 1 region. We're going to integrate y first, then x. This tells me that the volume of the prism that we created there, cleverly, triangle, 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 that prism, syncopated algebra, is equal to what? This is the double integral over the region D of the surface 3 minus x minus y dA. And that's what we're saying. We're cleverly, the problem is phrased the volume of a prism as the double integral of this surface, which is again the volume below this surface and above the region D. What is D? This triangle. So after figuring out what the bounds of the triangle are, this double integral by the strong Fubini's theorem. I'm not doing it in Italian, I'm English. Fubine forte. After we do that one, after we do this, what are we going to get? The integral from 0 to 1 of the integral from 0 to x of 3 minus x minus y dy dx. And now this one shouldn't give me hot fractions like I got in the last video, because we have linear, so it shouldn't be too bad. Well, we'll see. Maybe not. This is equal to the integral from 0 to 1 of, remember we're doing y, so this is going to give me 3 minus x times y. That whole thing is a constant. Do each one separately if you want. And then minus 1/2 y squared, evaluated from 0 to x dx. Cleaning that up and putting that in there, I don't have to put the 0 in there, but I'm going to get that this is the integral from 0 to 1 of 3 minus x times x minus 1/2 x squared dx, which is moving that up. This gives us, simplifying first, I'm going to get negative 1/2 x squared minus x squared plus 3x dx from 0 to 1. Don't forget your limits of integration. This gives me, by the fundamental theorem of calculus part 2, negative 1/2 times 1/3 x cubed minus 1/3 x cubed plus, what do I get? 3 over 2 x squared, evaluated from 0 to 1. Maybe I should combine that first. What did I get? We need a common denominator there, 2 and 2. And so what am I going to get? I'm going to get negative 3 over 6x cubed, which is going to give me 1/2, plus 3 over 2x squared, evaluated from 0 to 1, which is going to be a whole lot better than last time. That's going to give me negative 1/2 times 1 cubed plus 3 over 2 times 1 squared, which is 3 over 2 minus 1/2, which is, it's a unit volume. It's a unit volume, units cubed. You can use this as your unit, how you would define unit volumes in 3 dimensions of any other object. This guy apparently. What? Never mind. Next question. Okay, let's do one more of type 1. We're going to, or from your point of view, you're going to have to decide whether it's type 1 or type 2. I can kind of see already, sort of, it gives you hints the way that they phrase it. This is y equals 0. This is x equals 1. So those ones are just straight lines, and I can't do anything with them. But this one is a function now. So when I'm going to draw the picture, even before I draw it, I suspect that I'm going to phrase it as y in terms of x, because they've already given it to me in the question. But we'll see. Sometimes they hide these equations in words, and then you have to put them, and then they make you choose. For us, what do we get? I'm going to quickly sketch the region first. The x-axis, the line x equals 1, and the parabola y equals x squared. They meet at 1 and 1. And this is x equals 1. This is y equals x squared. This is y equals 0. That says 0 is less than or equal to x is less than or equal to 1. And then my y coordinate is going from 0 to the parabola x squared. This is my region D. Once I do that, that tells me that the double integral d of x plus 2y dA is equal to the integral from 0 to 1, the integral from 0 to x squared of x plus 2y dy dx. If I want to remind myself, I put brackets. I'm holding x constant. I'm integrating with respect to y. This gives me the integral from 0 to 1 of xy plus 2 over 2y squared, evaluated from 0 to x squared dx. That now gives me, cleaning that up, the integral from 0 to 1 of x times x squared, which is x cubed, plus, that gives me 1, and I get x squared squared, so x to the 4 dx. That's not too bad. And then, yeah, the common denominator should be 20, because it's going to be a 4 and a 5. This equals, what? You'll see in a second, 1 over 4, x to the 4, plus 1 over 5, x to the 5, evaluated from 0 to 1. I'm going to need a common denominator of those guys, which is going to give me 1 over 4 plus 1 over 5, which is equal to 1 over 4 times 5 over 5, plus 1 over 5 times 4 over 4, which is 9 over 20. Now let's do one of type 2 region. Example 3, compute. We'll describe that with some triple integrals one of these days, rotations and stuff, and the angular momentum and these types of things. Compute the double integral of xy if D is a triangle bounded by the lines y equals 1, x equals 2, and y equals x. Let's draw that region first. It's telling me 1, 2, 1, 2 possibly, and then what's going to happen, I have the line x equals 2 is this guy. The line y equals 1 is not the x-axis, finally it's that guy. And this one. And then I'm going to guess y equals x is this guy. It's going to go right through here, and it was supposed to pass through 1, 1, get there. There's the dot, and then I'm going to guess that's what? That's 2. Close enough. And then what does that say? When x is 2, y is 2, and then so this is our region D. This is what they're talking about. And again, often, this is the hardest part a lot of the time with any of these things, is taking that stupid word problem, the way they've hidden the object that you have, and trying to describe what it is. This is what they have. What are our bounds now? That's saying we have type 2 as promised. We're saying y is going from 1 to 2. And then now x is going from where? X is going from, it has to be this one minus this one. Or what is that going to say? That says y is less than or equal to x is less than or equal to 2. This is x equals 2 and this is x equals y. Tilt your head 90 degrees if you, it'll rectify that for you. Pun intended, rectify. This tells us that we get the double integral d of xy dA is now equal to the type 2 region. So I get the integral from 1 to 2 of the integral from y to 2 of xy, and this time dx dy. I put the brackets for myself to remind myself now this time it was type 2, so I'm holding y constant and I'm integrating with respect to x. That will give me equals the integral from 1 to 2 of y over 2x squared evaluated from y to 2 dy. That gives me equals the integral from 1 to 2 of y over 2 times 2 squared minus y over 2 times y squared dy. Equals, cleaning that up, this is equal to, I can pull 1/2 out of there, so I will, the integral from 1 to 2 of 4y minus y cubed dy, which is 1/2 2y squared minus 1 over 4y to the 4 evaluated from 1 to 2, which is going to equal 1/2 2 times 2 squared minus 1 over 4 times 2 to the 4 minus 1/2 times 2 times 1 squared minus 1 over 4 times 1 to the 4, which is equal to what? Get out of there, Stormy. 9 over 8. Please subscribe right here and hit the notification bell. You get notifications for this series and a bunch of other ones. Next time what we're going to do is we're going to do properties of double integrals and then do a couple more examples with these properties.